We've established Euler's first law for rigid bodies, which gives us the following relationship. And here we have F sub g is all the forces on the rigid body. We have the total mass of the rigid body and the acceleration of the rigid body of the center of mass as observed in the inertial reference frame. And so using this, we can calculate the equations of motion that govern transitional or the translational states. So this would be x and x dot, y and y dot if we're using Cartesian coordinates. So now we tackle Euler's second law, which governs rotational motion. And in planar motion, which we're constrained to, this provides one additional second-order differential equation that governs the rotational state, so theta and theta dot, for a rigid body. We'll start this analysis by looking at the total angular momentum of a rigid body. Now we've defined our rigid bodies as a specific case of a multi-particle system. And in this multi-particle system we have at least three masses that are non-collinear and then have a fixed distance with each other. When multi-particles have a velocity, we can calculate the total angular momentum, which we've seen before from Chapter 7. And this is total angular momentum about an inertially fixed point. And so for a rigid body, we change this discrete addition into a continuous integral. And in our continuous integral, we're integrating across the entire body for each differential mass. And that's the position of each differential mass with respect to O, crossed with the velocity of the differential mass with respect to O as observed in the inertial reference frame. Now we'll continue using this discrete representation of the total angular momentum in this derivation for simplicity. Now recall from particle dynamics that we can describe the linear momentum or angular momentum of a particle or a system of particles, but then to determine equations of motion and get dynamics, we would take the time derivative of our momentum. So we'll take the time derivative, the inertial time derivative, of the angular momentum. And we get this expression, which is the same that we saw in Chapter 7. And so we have two parts here. The first that we recognize pretty easily as the external moment about point O due to all the external forces that are applied to the body. And then the second term deals with our internal moments of the system. And so we said earlier in Chapter 7 that in most multi-particle systems that we deal with, this term is simply going to zero because there are no internal moments. But we know from statics that there are internal moments in rigid bodies. So recall that if you have a beam, we can cut the beam somewhere about the beam. And when we cut this and show the section, we have an axial force, we have a shear force, often denoted by a big V, and then we also have a moment. And this is the internal moment, the internal shear, and the internal axial force. And so these internal moments, if you recall from statics, cancel each other out and their sum is always equal to zero within the rigid body. And so when dealing with rigid bodies, when taking the time derivative of the angular momentum, we do have internal moments, but because they cancel, we're justified, even more justified now, of setting this term equal to zero simply because they cancel. And I should point out that in contrast to statics, where the moment was static, it stayed the same, and the shear stayed the same, it's in these dynamic systems of rigid bodies that you can plot the internal moment over time, let's say in a machine or in machinery, and this then introduces some aspects of machine design, which we'll see in another course. And so now that we've gotten rid of this second term, we have Euler's second law, which states that the rate of change of the inertial angular momentum of the rigid body about point O, and point O is fixed in the inertial frame, this is all equal to the total external moment about point O that acts on the rigid body. Now it's also important to point out that Euler didn't derive this law. He simply stated it axiomatically and did the same thing with the first, and this is much in the way that Newton stated his second law of inertia, and then tested it. And so we've seen this expression before. We saw it in multi-particle systems, and now we've translated this now and are applying this to rigid bodies. And so all the same caveats apply, such as conservation of angular momentum, which is where we say that the total moment, external moments on the system are equal to 0, and so angular momentum is conserved. Now this expression becomes a lot more useful when we apply the principle of angular momentum separation. And what we're saying with angular momentum separation is that we can divide the total angular momentum into two parts. The first is the angular momentum of the center of mass with respect to an inertially fixed point O, and then add to that the angular momentum of all the differential masses that are about the center of mass. And we see these expressions here where we have the total mass multiplied times the position vector of the center of mass with respect to point O crossed with its inertial velocity. And then the second part, the angular momentum about the center of mass, is a continuous expression. Now to get the dynamics of this, once again we take the time derivative as observed in the inertial reference frame. And the first term in this expression, the time derivative of the angular momentum of g with respect to O, is equal to the moment of g with respect to O. And so this is the cross product of the position vector of the center of mass with respect to O cross with F sub g, which is the sum of the external forces. And so let's look at that on a rigid body. Here we see a rigid body that's located in an inertial reference frame that has a center of mass location g, and then 3 forces applied. And of course this can be as many forces as needed. But this expression itself, we have a position vector of g with respect to O, and then F sub g will be equal to the sum of each of these forces. And so now let's examine the second term, which is the time derivative of the angular momentum about the center of mass, and this is equal to m sub g, so the moment about the center of mass. And we'll define this as I is equal from 1 to n of r I with respect to g cross with f sub I. And this is the moment due to each of these external forces that we have applied to the rigid body. And the position vector, r of I with respect to g, is showing us these position vectors. So this would be r of 1 with respect to g, r of 2 with respect to g, and this would be r of 3 with respect to g. That indicates the location at which each of these external forces is applied to the rigid body. Now this is the most common application that we'll see in this course, in which we have our moment about the center of mass defined in this normal way that we've calculated moments about points. However, if we're dealing with force fields such as big gravity, then we have to deal with the shape and the location and the orientation of the rigid body, and so then we have to apply a continuous definition for this moment about the center of mass. So in summary, we developed Euler's first law in angular momentum form, we have Euler's second law, and now with respect to the center of mass, which gives us a good tool. And so we're building out our toolbox. We're not quite ready to calculate equations of motion yet. We still need to deal with how to calculate the angular momentum of these rigid bodies, and we'll be doing that in future topics.